Hi all, thanks very much for the opportunity to speak. It's a little bit intimidating because I believe that there are 8 different faculty in here representing 4 departments who taught me. So as a consequence of that, it's intimidating. But in any event, I'm going to be telling you a little bit today about how you can use measurements in atomic systems to learn things about the universe as a whole. These are big questions, I would argue. What it means to be a big question, I think actually a lot of people can agree on. Things like, why are we here? I would argue for those of the younger folks in the audience that most good answers to that question come from people like Gary Larson and Bill Watterson, who sadly are no longer publishing. But in any event, things like why are we here, what else is out there with us, and that's what I'm going to try to talk about today. Here's a simplified history of the universe. The Big Bang happens, and as far as we understand it, Big Bang produces matter and antimatter in equal amounts. So, okay, well, what does that mean? So, matter is the stuff we're made up of. Antimatter, for the purposes of today's talk, there are people in the audience who would beg to differ with this definition, but it's the same stuff where you flip the charge, from plus to minus on all the little bits. So, an electron suddenly has a positive charge instead of a negative charge. We call it an anti-electron or a positron, etc. And Dave and others would probably highlight the asterisk, but I'm not going to bother. And essentially, what we care about for this talk is that if you have a matter particle and it comes in contact with an antimatter particle, the two will do what physicists refer to as annihilate and just become pure energy, and the mass is now gone. And if you've read the works of Dan Brown, for example, then you've seen information about this. But that's all I care about for this. So we have antimatter and matter in equal amounts after the Big Bang. And of course, it turns out that energy can turn back into matter according to E is equal to mc squared. So when the energy sort of density in the universe is high enough, we can turn matter into energy and back. But as the early universe is expanding, it cools. And eventually, the sort of ambient energy density is too low to do that anymore. And so at that point, we can't make matter out of energy any longer. And you would expect that this process of having matter and antimatter annihilate into energy should be the only process. And so we'll get left with a bunch of energy. There's no matter or antimatter left. The leftovers become what we call the cosmic microwave background radiation. And that's it, right? End of universe. And the problem with this picture, it's actually surprisingly close to accurate, except for the fact that apparently there's something left over, which is not just energy out there, right? It turns out not to be just Williams College, but that's one of the examples of things that are out there, right? So we need to revise our picture of the universe at least a little bit. And so it turns out that nature, at some level, places its thumb on the scale, right? And although we might make matter and antimatter in the Big Bang in equal amounts, there's a little bit of a favoring in this process that favors ordinary matter, which unfortunately we're not going to have too much time to talk about that process today, unless you ask me questions about it. I have a bunch of extra slides that I had to cut. But in any event, so that happens, and it means that when we have matter and antimatter annihilating into one another, there's a little bit of matter left over, and that's what we see around us, right? So this is now our revised, simplified history of the universe, okay? And the question is, why does this happen, right? Because if it didn't happen, we would not be here. So you should care about this question, right? So that's one of our questions. I mentioned the cosmic microwave background at one point along the way. And it turns out where this really comes from is, so we have all this energy, right? And I mentioned the universe cooling enough that we can't make matter out of it anymore, as a general rule, right? But it turns out there's still some other stuff going on. The matter which remains can interact with the energy in other ways. I can have particles that can exchange energy with one another and with the sort of background field, until at some point the cooling of the universe is sufficient that the ambient energy density is too low to any longer excite transitions in a hydrogen atom, right? And that turns out to be pretty much all that's around at this time, right? And at that point, this is when the cosmic microwave background actually gets sort of frozen into its final form, is when the energy no longer is interacting with the matter. Up until this point, the matter and the energy are in thermal equilibrium with one another, okay? Sort of exchanging things back and forth. And at this moment, which turns out to be a while after the Big Bang, that's it. And so this process, this thermal equilibrium, is the same thermal equilibrium you see if you have anything hot, right, that glows, something like a piece of steel that you pull out of the fireplace or something like that. It's what's called blackbody radiation, right? And we can measure the results of this process with satellites, right? It turns out this curve here is what you expect if you've taken, you know, an introductory physics class for what the color versus the energies and things like that and the amount of this radiation should be. And it turns out the error bars in this curve are actually 400 sigma error bars. So this is a very precise curve between the actual data and the theory, okay? So that happens, and this fits to about a 2 3/4 Kelvin temperature, which is what happens if you have, you know, the hot energy of the early universe cooling steadily over the last 14 billion years, okay? We get to this, and so if you look out at the sky as a consequence of this radiation being left over you know, from the Big Bang, basically, you can imagine, okay, so this is the globe, right? And if you look at the globe from the outside, it looks like this. But you could imagine also looking at it from the inside, right? And it would look much the same. It's just you'd see the underside of the continents at some level, right? So imagine that. But now we're going to be doing the same thing looking out at the sky around us. So that's kind of like looking at the globe from the inside. And if you do that, based on my discussion here, we should see basically the same color, as it were, the same energy everywhere, right? And it's about 2.7 Kelvin, okay? And that's actually pretty close to true, right? But it turns out that there are very small fluctuations in that effective temperature, if you like the color of the radiation, depending on where you look. And so if you look a little bit more closely, you see a picture that looks like that, where the red splotches are just a little bit warmer than 2.7 Kelvin, and the blue splotches are a little bit colder than 2.7 Kelvin. You know, parts in you know, a few parts in a million kind of temperature differences, things like that. And that's fine. So that's what the cosmic microwave background looks like. But you might say, well, okay, why are there red dots where there are versus blue dots where those are? And it turns out you can fit this curve using what's called Fourier analysis, for those of you who have taken some physics or math classes, and try to model the shape with what's called a multipole expansion. And you can do that, and it gives rise to a curve like this. And the details of this are not particularly important, except for the fact that the particular shape of this curve, which of the so-called multipoles are dominant in this picture here, right, you'd like to try to explain with what we know about the universe, okay? And if you put in a really simple model, you can't make the curve look like this unless you put in some extra stuff in the universe beyond the matter you see when you look out at the stars with a telescope, okay? We call that dark matter simply because you can't see it with a telescope, so apparently it's dark, right? And as you vary the density of this dark matter in the universe, the relative heights of the various peaks in this curve change, right? That's the only detail that matters to us right now, is the change in the peak heights as I vary this stuff that's out in the universe. So not only do we not know why we're here in the first place, we also don't know, beyond the fact that there must be something else out there, we don't really know what it is, right? And there's other data about this, right, for other evidence for dark matter, which is also pretty easy to understand. If you've ever studied any physics, you might know that if I have two masses, they attract. That's what we call gravity. And it turns out that force, which is, you know, sort of between the two masses, you can also call a centripetal force, right? If you have my Earth going around the sun in a circle, right? The forces between them are center-seeking, so we call it a centripetal force. You can work out the math, and it turns out for a point mass, then we expect to see a velocity which is of the little mass m, say the Earth going around the sun, which is related to the mass of the sun and how far away we are. Okay. You can think about this and consider limits. If the big mass in the center of the sun is effectively a point mass, all the mass is concentrated in one space, then we get this 1 over the square root of r kind of dependence. And that's basically almost perfectly describes the mass and speed relationship of all the planets in the solar system. It's this 1 over r to the 1/2 kind of relationship. Okay, it's not exactly 1/2, but that's in part because the solar system is not a perfect point mass, right? The sun is extended, and there are other things in the solar system besides just the sun. Not many, but a few, right? On the other hand, you could imagine, instead of having the sun all kind of localized in the center of the solar system, you could imagine all that mass being smeared out in space uniformly, right? And think about what would this kind of behavior look like if the mass was smeared out in space. And if you do that mass, those of you who have taken Physics 201, you did this calculation, but with charge instead of with mass, right? But it's the same kind of force law. It's a 1 over r squared force law. Okay? And then you discover that the velocity of your particles, as you move further away from the center of the distribution, should go faster and faster and faster in their orbits. Okay? So, fine. those are some limits. We can actually go look at stuff in the sky and see what does it do. How fast does it move as we move out from the center of some solar system or galaxy or something like that? This has been done. So this is the Milky Way if you take a picture of it with a telescope. And you can see that there apparently is a bunch of stuff in the middle, and then there's less stuff as you move farther out. So it's not exactly a point mass, but it's certainly not a uniform mass distribution either. Okay? We can think about, in this case, integrating over the mass distribution instead of calling it a point mass or a uniform distribution, and say, okay, what does that mean the velocity should be as we move out from the center of the galaxy? And this is kind of what you would expect, right? Near the middle, you might say it's pretty uniform, and so I should have this rising velocity as I move out from the center. And then eventually, when most of the mass is sort of inside of the radius of our orbiting object, we should be looking at that point mass kind of limit, and then we should see this kind of falling off curve, this 1 over r squared kind of behavior, right? So that's kind of what you would expect to see for velocities of stuff as you move out from the center of a galaxy or a solar system or something like that, right? And it turns out this measurement was done for the first time in the 1970s, principally by a brilliant astronomer named Vera Rubin. And this is what she found, along with Kent Ford, which is that you see this rising velocity. So forget about the left-hand side of this plot for the moment, right? As you move out from the center of the galaxy, which is 0, you see this rising velocity. That's what we expected from this curve back here. But it doesn't fall down again anymore, right? And in order for it to not fall down again anymore, there needs to be more mass spread out from the center of the galaxy. We can't treat it as a point mass no matter how far out we go. And that's weird, because when you look at the picture of the galaxy, there's nothing out here, right? So what's going on? Well, this is another piece of evidence for this dark matter that we can't seem to see with the telescope, but it certainly is impacting things like the cosmic microwave background, as well as these so-called galactic rotation curves, right? So if you look a little bit more carefully, this is more recent data, right? And you try to map what you would expect the rotation curve to be as a function of the gas in the galaxy that we can actually measure with a telescope, all the stars in there, right, et cetera. You'd get these two curves down here. The actual curve is this rising one. And so in fact, not only does there need to be stuff out there that we can't see with a telescope, but most of the stuff that's out there we can't see with a telescope, okay? So that's a little bit weird. 85% of the stuff in our galaxy is apparently not the sort of normal matter that we interact with on a daily basis. And that's weird. And so what we're going to talk about in terms of the rest of today is trying to answer these two questions, right? The why are we here question that we talked about, and the sort of what's out there question. And at some level, we've already formed a rudimentary answer, right? We said there's some kind of an asymmetry in the evolution of the early universe, and we've also said apparently there's dark matter. But that's not an answer at all. It's like we have an answer to a question because we declared it to be the answer, but there's nothing behind this, right? It's like this must be true, but we have no idea why, okay? So how can we learn more to actually sort of get a more satisfying answer to the questions besides this must be true, 'cause, right? And there's more than one way you could try to tackle a question like this. One of the ways people try to tackle questions like this when they're searching for new physics is they try to see it directly, right? What we're talking about here, for example, in this idea of the asymmetry and the evolution of the early universe, if you want to measure that, one nice thing to do would be to try to create conditions which are similar to those in the early universe and see what happens, right? And that's, at some level, is what happens in, for example, particle colliders like CERN, right? Or if you want to look for evidence of dark matter, you could literally just look for evidence of dark matter and see what you see, right? And it's not so clear how you might do that, but if it interacts maybe weakly with normal matter, you get a whole bunch of normal matter together, and you look to see if it does a dance on Thursdays or something like that, right? To see what kind of behavior is going on. And these are fantastic experiments. We've learned a ton from these kinds of experiments over the years, but there's a small drawback for doing this kind of work. The annual operating budget of the Large Hadron Collider at CERN right now is roughly $1 billion, okay? And CERN at this point is built out to its present extent. They're going to continue to take data with it for another decade or so, but at that point it will have done for us what it can. And what I'm drawing here, so actually CERN is this little circle over here. The dashed circle here is what's called the Future Circular Collider. It's a proposed collider that might get built in the second half of this century, right? Presently, the proposed budget for it is $20 billion, and if you believe that, I have a bridge to sell you, because there was another collider that was being built in the United States starting in the 1980s called the Superconducting Supercollider. It was canceled early in the Clinton administration in 1993 because that budget, which was about the same size scale as this one, had already climbed past $12 billion, and that was now 35 years ago, right? So I don't know where the CERN people came up with this number, but I don't personally buy it, okay? This experiment here, which is basically to zeroth order a big bucket of liquid argon buried inside of a mountain about 2 kilometers deep, has a low budget of $200 million, but it's still expensive, right? So you can learn a ton from these kinds of experiments, but you have to really commit to them, right? The other way you might try to answer these questions is to say, well, okay, if this physics was true in the early universe, it is still true today. Right? We don't think that physics has changed over the history of the universe. It's just that the environment in which we're looking at it is not the same, right? Because the universe is cold by some definition today versus then. But if the physics is still true, it should still have subtle, tendrils going out into the physics we see on a daily basis. And if you look closely enough, you might be able to measure some evidence of it and learn about what was going on in the early universe, right? So the so-called ACME experiment, which is going on at Harvard, as well as other experiments like it, are looking for the kind of physics which would be relevant for understanding this matter-antimatter asymmetry. The size scale of this is not 30 kilometers, but more like sort of room scale. And the budget for this is not, $100 billion, but, I don't know, less than that. Probably, I don't know what they spend at that experiment, probably a couple $100,000 a year to fund graduate students and postdocs and things like that, and occasionally buy a new laser or something. And then, we're also doing work in my own lab here at Williams with just a handful of trapped calcium ions, where we're trying to learn something about dark matter, and I can assure you that my lab does not spend $100 billion. So this is what we're going to talk about for the rest of today, is this idea of trying to look for evidence of the physics of the early universe and of dark matter that's out around us, in the physics that is sort of all around us all the time. But the tricky thing about that is the effects are small, right? I don't know how small, because we haven't seen them yet, but they're definitely small, so you have to figure out ways to be able to look carefully so that you're not sort of masked from the physics you want to see by all the sort of everyday ordinary physics which is, which we're used to, okay? So to try to get at exactly how hard this is, though, let me note that the physics which, the current state of the art of this measurement at Harvard is looking for, apparently this is an older version of the talk. It's trying to make a measurement which is hard to make. But in any event, to try to show you how hard, let's think about nursing, right? Some of you in the room may have done this at some point. My wife did for my daughter, and one of the concerns that my wife and I think many mothers have early on when their child is a newborn is my child getting any food, right? This is an important question, I would argue, right? And one of the ways that people try to answer this question, since babies don't answer it very effectively on their own, is you weigh the baby, you then feed the baby, and then you weigh the baby a second time. And if the baby is heavier, then you assume that the baby has eaten something, right? And then you say, fantastic, and you hand the baby to your husband or your significant other, and you go to sleep, and then you do it again a few hours later, right? And that's great, but there's a challenge here, right? In order to do this, you need to be able to measure your baby's weight pretty carefully, and according to people in the medical community, it's not a very good idea to try to rely on this measurement, and the reason why is because you're trying to measure a small amount of weight increase on, by relative terms, a large baby, right? What do I mean by that? Well, let's suppose that your baby weighs about 10 pounds. That would be a large newborn, but certainly well within the realm of possibility. And at a typical feeding, they might consume maybe of order an ounce of milk, so that's about a tenth of a pound, which means that if you want to get a precision of 10% on how much they actually consumed, right, you need a scale which can make a measurement which is precise at the level of about a part in 10 to the 3, something like that, right? It's doable, but you need a pretty good scale, and you also need a baby that doesn't move, right? So it's tricky, right? That experiment, the state of the art for these kind of atomic physics-based probes of things like matter-antimatter asymmetry is not a part in 10 to the 3, it's a part in 10 to the 18, okay? So to give you a sense of what that actually means, let's imagine the same problem. I'm trying to figure out how much baby is consumed, but instead of trying to measure how much milk my baby has eaten with the baby as this sort of anchor around the measurement, we have a container ship, right? This is the Ever Given, which got stuck in the Suez Canal a while back that helped to contribute to the supply chain crisis. It's big, right? Just in case you hadn't gathered that, this is like an excavator of the type that was outside by the Davis Center earlier this semester, or last year, or whenever it was, right? Here is a baby, okay? This is not to scale. That is a little bit closer to scale, but I couldn't actually make the baby small enough and still be able to see it. But you get the idea, right? But we're not there yet. This container ship is big, but we need a few more. But actually, we're still not there. So each one of these grids, put it in one of these, right? That's what we're trying to do, is measure the milk, not the baby, the milk consumed by the baby, while that baby happens to be sitting on 1 million of these container ships, right? You need a pretty funky scale to be able to make that measurement, right? Clearly, it's not going to be practical to do that. So what you need to come up with then is a way of not doing that measurement, but still getting the answer that that measurement would reveal if only you could do it, right? You need a way to ignore the container ships, and also the baby for that matter, and only measure the milk, right? And the obvious answer would be, well, you give the milk in a bottle, right? But that actually doesn't work either, because half the bottle is like spat all over your shirt and things like that when you're trying to feed your child. So it's a hard problem, right? And it's also a hard problem in atomic physics. So the basic idea then is you're trying to figure out how to make the thing you want to know stick out like a sore thumb relative to all of the standard model, we call it background, right? The container ships in the measurement, okay? So here's an example. This is a bunch of penguins, okay? And it may or may not be obvious to you that that's true, but it's like, okay, I want you to pick out the important penguin, okay? Penguins are all black and white, right? They all look the same, except it turns out that most of these penguins are children, and one of them is not. And when the penguins get older, they have different coloring than they do when they're children. So in this picture, the special penguin is somewhat obvious, right? In this one, not so much. So we need to figure out the right filter for our measurements that actually gets us to this kind of a picture instead of that one, okay? That's what basically precision measurements in atomic physics are all about, is how do you cast your measurement into this picture so you can just walk up to the penguin you care about and say, hi, is your name Ephraim? And if the answer is no, then you go, like, whatever, find a different penguin. I don't know what you do, right? So we're going to talk about this kind of a measurement, okay? And we're going to talk about it in the context of searching for dark matter, which is what we're doing with one of the measurements going on in my laboratory, okay? So I know very little about dark matter. Much of what I know is from reading review articles like this. Those of you who are, like students in the physics community, this journal is fantastic, Review of Modern Physics, because it's written for people who are not specialists in that subfield. So read it, right, if there's a thing you want to know about it. There's probably an article out there, unless you've come up with a novel idea that literally no one has ever thought about before, in which case, kudos to you. But, so what is dark matter? Well, like I said, I don't know. But fortunately, I don't feel so bad about that because neither does anyone else, okay? But what we do know is that it doesn't, you might say, well, okay, you can't see this stuff with a telescope, but maybe it's just because your telescope isn't good enough or whatever. But there's good reason to believe from astrophysical data that it's not just, ordinary matter that is hard to see with a telescope, right? There's more to it than that, okay? There's some data out there that suggests that it might be something that the people in the community refer to as a weakly interacting massive particle, okay? Also known as a WIMP, which leads to these great ideas of nerds searching for WIMPs and things like that. But this is the kind of work which is searching for this stuff is what you do with these basically, like mountains full of liquid argon and these kinds of things. And one of my colleagues in the physics department here is involved with this measurement. So if you want to know more about that, I encourage you to talk to Graham. He's literally at the mountain right now in Italy on sabbatical, so you'll have to wait. But Graham has lots of things to talk about that. This is not what my lab is looking for. My lab is looking for what you might call light dark matter, which is a stupid title, right? But what we mean here is dark matter particles which are not particularly massive, okay? Not that they are light in the sense that you can see them, but not heavy, right? It's a hard thing to look for, right? But if you think about what such a particle might do when it comes to looking at structure of an ordinary atom, it turns out that if there was a low mass dark matter particle, right? It would probably have some kind of a fifth force carrier associated with it, right? Which would lead to what we call a Yukawa type interaction. And the details of this don't matter, right? But this is what a Yukawa interaction looks like. And all I care about right now is the fact that it's going to interact with normal matter, okay? And so it will interact, among other things, with electrons. So that strength of that coupling is what we're going to call Y sub E. It might also interact with the neutrons in the nucleus of an atom, which we could call Y sub N. And it turns out it would interact with the protons as well, but that's irrelevant for the type of measurement that my lab is doing, okay? So this is the kind of interaction that we're looking for. And what matters here is that if you look at what's called an isotope shift, you can get some sensitivity to this. So what is an isotope shift? Well, hold that thought, okay? It turns out that if you were to measure such a thing, right, the influence of this interaction on your atom would be to change the energy levels of all these different things in the atom by just a little bit in a way that depends on how strongly does this dark matter that we don't know about couple to the regular matter, And also, how many neutrons do there happen to be in your atom, right? This is what we're going to be looking for, plus a bunch of stuff having to do with regular physics that is hard to calculate, right? Okay, fine. So what is an isotope shift? Well, as you may have learned in a high school chemistry class or something like that, an isotope of an atom is just referring to a particular number of neutrons in its nucleus. So if I want to talk about, I don't know, aluminum or something like that as distinct from iron, the thing that makes those distinct on the periodic table is the number of protons they have in them, okay? But I could have aluminum with, I don't know, however many protons it has, apparently 13, and I could have aluminum with maybe 10 or 11 or 12 or a whole bunch of different numbers of neutrons in the nucleus. They're all still aluminum, but they're a little bit different, okay? So those are different isotopes of an element or of an atom. And if I go from one of those isotopes to another, all I'm doing is literally looking at another example that's got more or fewer neutrons in the nucleus. So imagine I have one isotope, I give it a few more neutrons, it's now a different isotope, and the question is, what does that do to the structure of the atom? Well, it makes it more massive because you put more stuff in there. Not so surprising. It turns out in general it also makes the nucleus bigger. Also not so surprising. And what is the impact of those two things? Well, cleverly, we refer to that as a contribution to the shift in the energy due to the mass. That's because you've made it heavier. For those of you who have studied a little bit of physics, if you think about the Bohr model, the reduced mass is actually a thing that shows up in the expression for the energies. And if I make the nucleus heavier, I change the reduced mass. Okay? It also turns out if I put some more neutrons into the nucleus, the protons, which are charged, also move around. And so the electric field of the nucleus is now a little bit different than it was before. And that change in the electric field means that the interaction of that nucleus with the electrons is also a little bit different. And so that gives rise to what we call a field shift because of this change in the electric field. Okay? Plus some higher order stuff that for now we're going to ignore. Okay? I can write down what this shift would look like. And we're going to choose to write it down in sort of a funny way, where we're going to think about the isotope shift is what this frequency is referring to, on some particular transition between levels that we're going to call A, between two isotopes that I'm going to call I and J. Again, this is not so important, but the key point is I'm going to get a mass shift, which cares about the difference between the masses of one nucleus and the other one of the two isotopes we're comparing, as well as something having to do with the size difference of the two nuclei that we talked about, right? Fine. And then some proportionality constants, basically, at lowest order, okay? Here's the same thing we just said. I've got the piece due to the mass, the piece due to the field, and then some other stuff, okay? But critically, the stuff in blue here, the mass difference, or actually it's a reciprocal mass difference, and the size of the nucleus depends only on the nucleus, right? And the red terms here, which have to do with how those changes actually impact the structure of the electrons, has to do with the atomic wave functions, okay? So the red stuff cares about the electrons, the blue stuff cares about the nucleus. Fine. I can't calculate any of that particularly well, okay? Nor, to the best of my knowledge, can anyone else, right? But here's where the cleverness, this idea of I want to find the colored penguin among all the brown penguins, comes into play. It turns out if I look at this same thing and I scale it in a particular way, I'm just going to divide by the quantity mu, I get an expression that looks like this. That's not clever. But it turns out now, if I just add and subtract the purple term from the equation, right? It's the same thing. I'm adding and subtracting it. So I've added 0. I'm allowed to do that, right, without changing anything. I can add 0, right? And I've rearranged things a little bit such that this expression is exactly the same as what I wrote down before, okay? Except for the fact that I'm renormalizing the second term here, and ultimately this here is the same expression that we had up there, but now measured on a different transition in the same atom. Why is this interesting? Well, it means that I can write down this isotope shift on one transition in terms of the isotope shift in a second transition. And this is just a constant, and this is the isotope shift in the second transition, and here's another constant. So it's a linear relationship, in short, between the isotope shifts on one transition and the isotope shifts on another transition. And this is where the sort of clever penguin coloring idea comes into play, is that if this is all the physics that's going on, and I measure the isotope shifts on one transition, and then I measure them on another transition, and I plot them against one another, it should be a line, right? That's what a linear relation means. And so if I do this and I see a line, then I know all the physics that's going on. And if I see something that isn't a line, then there might be something subtle going on that we have to look into, right? So here's an example of this. Before the work that my lab has been doing got started, this was, to the best of my knowledge, the most precisely known one of these plots that have been made. And look, it's a line. Not so exciting. There's no new physics here, okay? But if you did see something that was nonlinear, the question is, what would it tell you about? Well, all those higher order terms that I chose to sweep under the rug must be leading to the nonlinearity that you would see. And some of those higher order terms are just sort of boring ordinary physics. But if there were new physics associated with this dark matter interaction that I mentioned, that would also lead to a nonlinearity in this plot. So if you can make these measurements and make this plot and see that it's curvy, right, then you can try to see whether or not you think that curviness is due to interactions with some hypothetical dark matter particle or just boring ordinary matter, okay? All right. You can calculate a lot of, at least with some precision, a lot of the ordinary stuff, so that even if you see a nonlinearity and you say, well, is it the boring stuff or the new stuff, you can actually start to tease those things out from one another as well. So this is what we do in my laboratory. Okay? We do this by trapping ions. In short, we've got a structure with a bunch of metal and insulator and things like that that gives us a bunch of electrodes that we can apply voltages to. When you apply the right voltages, you get some particular electric fields in which you can trap an ion, and then these are the particular transitions in calcium that we're going to drive to actually manipulate these things. Okay? So to give you a little bit more detail, what we're interested in doing is measuring isotope shifts on transitions between this ground state and these states here. And I'll talk a little bit more about why that's useful and relevant later on, but it turns out that these happen to be transitions you can measure with very good precision, which is what you need to learn things about the colored penguin here, even if you have the idea of looking for a line versus not a line, okay? So that's what we're measuring. How do you do this? Well, you need to start by having ions that hang around in your laboratory for long enough to be able to measure something with them. And that's not obviously easy because ions are charged, and if there's any electric fields around, which there always are, they just feel the Coulomb interaction, the force, and they go someplace, right? So we need to come up with our own fields that will trap the ions in space. And the problem is if I have a positive charge like this and I want it not to go anywhere, I'd love to apply an electric field to it that pushes in from all directions to hold it still. And unfortunately, what's called Gauss's law, one of Maxwell's equations, says, sorry, that's not possible. Physics does not allow for that. So the best we can do is we can make a field that points in some directions and out in others. And that's problematic for holding onto an ion because I keep my ion from going up and down in this picture, but it tends to get squirted out to the side, right, which isn't so good if you want it to stay where you put it. But it turns out if you make the field oscillate, then you can actually hang on to it. You wind up getting a potential landscape which looks like an oscillating saddle potential in this case, right, something like this, where the ion is going to stay right at the middle. And any of you who are clever, you'd say, but wait a minute, at any given moment it can always roll downhill and leave, so that clearly will not trap your particle. I claim you're wrong, right? And the reason why I claim you're wrong is because here's an analog to this. This is not electric fields, this is gravitational interaction, right? But here is a saddle potential in gravity, right? Basically, you'd say I put a ball on that, it should roll down the hill and not stay, right? But it turns out if you make the saddle spin, that's analogous to the sloshing of this potential that we were describing here. And it turns out, please work, this is always the stressful part of giving talks, is you rely on pieces of technology that, like the spinning wheel is not that exciting to watch. Okay, here we go. So the ball goes on there, and it doesn't roll off the side, right? So it turns out we can use this same kind of behavior with an oscillating electric field to trap our ion in the laboratory, okay? All right, so we can trap an ion. No, I don't want to do that anymore. Now I want to go somewhere else. Ha! Victorious. All right. So we need to create some structure that will give us these electric fields to hang onto the ions. So how do we do this? Well, we need an ion in the first place to trap it. So we start with a neutral atom, right? We make neutral atoms by starting with a metallic sample. You heat it up. Some of the atoms come off as a gas if you get it hot enough, right? You can then zap it with a couple of lasers to rip off one of the electrons, and now it's charged, and it will feel the electric fields. And if you do this in the right way, if you rip the ions off the electron off in exactly the location where the fields are to trap it, it ignores the fields on the way in because it's neutral. You rip off the electron, now it's charged, and it says, oh my God, I'm stuck in a box. I don't know what that sounds like in the language of an electron, but it works. So this is effectively what we have in the laboratory. If you want to actually measure something with it, what you have to do is then make the ion glow, and you can do that by driving a transition with a laser to take the electron, some other electron that's still in the atom, up to an excited state, and when it falls back down again, it spits out some light, which you can then collect with a lens and image onto a camera. And if you do that, you get a picture that looks a little something like this, where the white dot there is light collected from a single individual, in this case calcium ion, superposed over kind of what the background would look like. And this is not, quote, to scale. The dot you see is related to the diffraction limit of the optics you use to collect the light. The actual ion's real size would be orders of magnitude smaller than this in terms of the relative scale. But this is what we can actually see. Okay? And the tools we use to do this are sort of standard in the community. It's basically a table full of lasers. The nice thing about doing this at a place like Williams is that building these lasers is a great student project. So all the ones with purple arrows were built by students over the years, most notably these three, who have gone on to do great things. We've got a fancy laser that we use to drive the transitions that we're using to actually measure the isotope shifts, which was worked on by a bunch of other students in the years past. And when we put all the pieces together, we actually get really good control over the ions. So Sierra Jubin was responsible for building sort of the assembly that the trap is in. And then once that was done, Ashe was the first one to trap ions in it and demonstrate that we could control them. So here we have a video that Ashe made years ago of this is a single ion being loaded into the trap. So you can imagine sort of behind the projector screen is an oven. There's neutral atoms coming sort of through the screen. We zap them with a laser, and the moment we get rid of that electron, they then see a different set of lasers and are resonant with them and absorb some light and then spit it back out again and start to glow. We then manipulate the electric fields in the trap by changing voltages on all the various electrodes to shuttle that ion from one side over to the other. And if we iterate on that process, let's see if I can get this to go again. Right? If we iterate that process a bunch of times, then we can build up a chain of individual calcium ions one at a time. So here's 2, and then we load another one into the chain, and now we have 3, et cetera. And when they're going dark there, it's just literally because the laser that illuminates them is being brought back over to here so I can see what's going on at the so-called loading slot of the trap. Okay? To then do a measurement with this stuff, we have to illuminate them with a bunch of other ions. Really what we're trying to do here, as I mentioned, is measure an isotope shift. So I need 2 different ions, right? Isotope A and isotope B trapped at the same time. We're going to illuminate them both with a laser that has a frequency that will talk to both of those guys at the same time and sort of see what happens. So we're going to drive this particular transition. The details aren't so important. But it turns out that this is also a real fun experiment to do with undergraduates because of the fact that the quantum mechanics involved in this system are really readily apparent. What do I mean by that? Well, let's suppose I drive this transition, okay? I might start with my electron down here, I turn this laser on, and I drive the transition to try to get the electron up into the upper state. But in fact, what I actually do when I drive that transition is excite a quantum mechanical superposition of some of the electron probability being down here and some of it being down there. And then what we want to do is measure what happened. So if I turn on these 2 lasers, okay, if the electron is down here, it's resonant with this transition, it absorbs that light and spits it back out again and glows, and I say, oh, look, there's a bright little dot in my trap. But if the electron was up in this state here, right, it ignores these 2 lasers and the ion stays dark. So if I have a quantum mechanical superposition with some mix of probability down here and up there, and then I turn on these lasers, I collapse that superposition in the lingo of quantum mechanics into either this state or that state, and either I see a bright spot with a bunch of counts, right, is what this picture is looking at, or I see a dark, an absence of counts, right? So here we're saying the number of experiments versus how many photons we collect. And if we collapse the ion into the bright state, we see a bunch. If it happens to collapse into the dark state, we don't see so many, right? And of course, if it's actually a superposition of those 2 things, then you get some admixture of these, where this is multiple repetitions of the experiment, each one giving rise to one particular measurement. And this is, I don't know, maybe 100 or 200 trials of the thing, okay? If I do this as a function of tuning the frequency of this particular laser, right, then basically I'll get some probability of bright versus dark. You can think about 1 on this would be dark, 0 is bright, and anywhere in between them is some mixture of those 2 probabilities, which is dependent on how successful I was in driving that initial transition to begin with. Okay? So one measurement of the experiment actually involves doing this simultaneously on multiple transitions in multiple isotopes. So there's some subtlety here that I'm not going to go into. But the moral of the story is that by making these kinds of measurements, I can actually figure out what the isotope shift was between a particular transition and one isotope versus the adjacent one, which is trapped at the same time. Okay? So we did this on one of these transitions, and we made one of these king plots where the horizontal axis is our data, and the vertical axis is another transition measured by somebody else. And you'll notice that A, it's still linear, but also B, the number of digits of precision of our measurement are somewhat larger than those of the other measurement. And if you really want to have a lot of sensitivity to whether or not this is a line, it would be awfully nice if you had a similar level of sensitivity for both of the axes, right? And so we did this measurement, and actually originally I didn't intend to get into this business to do this at all. We were doing these measurements for a completely different reason. But when we learned about this application, we said, oh, maybe we should do more. And further, another group measuring these same kinds of things in a different ion entirely, this is a terbium instead of calcium, which is what we use, saw evidence of a nonlinearity, right? These points don't lie on the line, okay? And it's like, well, okay, why didn't you see a nonlinearity? Well, it turns out, in a terbium, if we go back to this plot, a terbium has a whole bunch of standard model ordinary physics that leads to nonlinear behaviors. And so the question is this nonlinearity boring physics, or have they seen evidence of dark matter? And if you can make a similar measurement in calcium, which has much less, right? 3 is much smaller than 12,000, right? Much less sort of boring physics involved in a nonlinearity. If you see a measurement at the same level of sensitivity that doesn't see something in calcium, but did in a terbium, then you say, sorry, a terbium, you're boring, and you move on, right? So that's what we started to do. It turns out, with some subtleties also about the shape of this nonlinearity, does it look like an S or a U, basically, you can learn more about whether or not the sources of nonlinearity are due to new physics, i.e. dark matter, or things within the standard model, okay? Further, there was another measurement made after hours in calcium that suggested that, in fact, calcium at a similar level of precision to a terbium was still linear, but we wanted to improve upon this. So we went ahead, we'd previously measured, this was the red transition I measured with Felix Nolman, class of 2019, and now we're working on measuring this parallel transition so as to have the two transitions we need to compare to one another to make the linear plot. This is much the same process with one exception. If I drive this transition in the same way we drove the other transition before, right, I excite some superposition of this ground state in this other excited state, the D3 half state instead of the D5 half state. And that's fine. And then we turn on our detection lasers, if you like, to see what's going on, and there's a problem, right? It turns out if I actually excite this transition that makes the ion glow if I collapse into the ground state, some of the time it decays back down into this state, which, by the way, is what we were now exciting into. And the difficulty there is, in order to get it back into this transition so that I can continue to make it glow to see what's going on, I have to turn on this secondary laser here, this 866 nanometer laser, which connects to the state that we're trying to excite to. And so if I drive this transition, no matter what the particular quantum mechanical superposition is that I excite of S and D, both of those states are involved in the fluorescence detection process, and so I can't tell if I succeeded or not, which means that we've wasted our time, unless we can do something to actually distinguish between the ground state and the excited state. So this makes us sad, but we can get away with, if we drive one more intermediate transition, we can drive from this excited state up to here. Some of the time the ion will decay back down to this state, and that one actually is the one that we were in previously. So with a sort of more convoluted process, we can find out whether or not we've succeeded in driving this so-called S to D3 half transition, okay? Unfortunately, this step actually only gets us to where we want to wind up 6% of the time. So essentially in doing this, we kill our signal to noise by a factor of about 20, okay? That's bad. But the good thing is that these particular kinds of measurement have such exquisite signal to noise to begin with that throwing away 19 out of 20 of it is actually not so bad, right? I actually am trying to analyze some of this data. I got in touch with Liz Upton in the stats department, and one of the comments she made along the way was, I have never seen data this clean, right? And it's because if you take data in the social sciences and things like that, it's always cluttered because they're cluttered systems. Atoms are beautiful, right? Everyone should be an atom, right? Right? None of this mole nonsense. One atom at a time is the way to go, right? So the question is, what have we learned? Well, this is the data from the previous calcium measurement that I mentioned that happened after our first transition was measured. And sadly, we haven't quite finished yet. We need at least 3 points to say whether it's a trivial line or not, right? 2 points I can guarantee you will be fit by a line, and that's what we have so far. But Timmy, who's here in the audience, he's measured this one and that one. You can see that they're sort of near where the other old measurements were. We're presently working on that one, and when it's done, I'll get back to you. There is some other stuff going on in the lab at the same time with a bunch of other students. We have work going on to try to show or measure sort of thermodynamics, basically, on microscopic scales. We're trying to build what you might call a thermal diode. So a diode, in its conventional parlance, is an object that will conduct electricity in one direction but not the other. And it's one of the critical elements that has enabled computation in the information age and things like that. In principle, you could build an object that conducts heat in one direction but not the opposing direction. And if you could do such a thing, there's actually an immense number of technological applications for such a thing. Now, to be clear, we're going to try to build one with 2 ions. There are no technological applications of a 2-ion thermal diode, right? But proving that it's even possible experimentally to do it in this system would still be useful. The best sort of solid-state physics example that's been demonstrated so far has about a 1% difference between forward and backwards conduction of heat, right? With ions, we should be able to do something that has more like, instead of a 1%, it would be about 100 or 150% change. So that would be an improvement. To be clear, the electrical equivalent is, I don't know, a gazillion orders of magnitude difference between forward and backwards. But even a factor of 2 or something like that, to prove that that's possible, if you could figure out how to build it on a sort of a pragmatic scale, there's a ton of places in the sort of energy infrastructure of the universe, or at least of humanity, where such a thing would be really useful. And there's a lot of stuff going on in the lab to support these kinds of measurements. But sort of a take-home measurement message here is that atomic physics experiments, even if they're self-contained in a little lab at Williams or elsewhere, are really powerful measurements for learning things about physics. And it turns out that even if you measure 0 in these things, right, you actually still have learned a lot about what's not out there, right? This idea of diagnosis by exclusion, right, is actually like half of medicine, I think, right? And it turns out to be a really useful thing in physics as well. So thanks to all the folks who have helped out with this over the years, and if anybody has a question, I will do my best to answer it. Thanks very much.
I have an unbelievably naive question. Thank you for the talk also. Where does the calcium come from? Or the deuterium for your colleagues? Like, do you have to put a little calcium chloride or something into your chamber?
Yeah, so it turns out, I mean, in principle, you could use calcium chloride, but what we actually just use calcium metal, right? Which, of course, is a reactive. So you have to, you can make calcium metal via some kind of chemistry in an inert atmosphere, and then if you keep it in an inert atmosphere surrounded by a noble gas or something like that, you'll keep just a pure calcium metal. If we stuff that into the vacuum chamber and then pump out all the oxygen in a hurry, then we can keep, it's still calcium metal with a very thin layer of oxide around the outside, and that's okay. If you heat it up enough, then you can basically crack that oxide layer to expose the calcium inside. And then when you get that hot enough, then calcium atoms will sublimate off of the metallic sample such that they're now a gas, and you can zap them with lasers and play with them. But it's literally just the same calcium that's in your bones and things like that, but as a pure metal instead of as a, whatever, hydroxyapatite or something like that. I don't know what it is in a bone, but yeah. Tim.
So for the video that you showed of the saddle
Yeah.
that trapped the ball, right? So I'm trying to wrap my head around, for your ion trap, should I be thinking of it, so I assume, so the lasers that you're using, is that what's generating the energy to show those shifts in transition, or are the lasers actually, should I be thinking of that as the spinning saddle?
Yeah, good question. And the answer, of course, is that it depends on exactly how you choose to do your work. You can absolutely build a trap which is analogous to the spinning saddle purely with a laser, okay? It's what's called an optical dipole trap. If you've ever heard the term optical tweezers, which play a role in biophysics and things like that, that's what's going on there. And they work beautifully, but the problem with an optical dipole trap is you're interacting an electric field of your laser now with a neutral particle, okay? And electric fields interacting with neutral particles are weak interactions, right? Because the only thing that happens is the electric field polarizes, it separates the positive and negative charges of the neutral particle and then interacts with that object, which is much, much less strong than an electric field interacting with a net charge, right? So although it is possible to do that, the strength of the interaction is small. So what we actually have is literally just a piece of metal, you hook it up to a battery to apply, to create a voltage, that creates an electric field, and then, by manipulating the voltages in the correct way, you can create, in principle, you could create a rotating field exactly analogous to the saddle, but actually what we do is we create an oscillating field. So instead of having the high parts and the low parts of the saddle doing this, and so intermediately, like sometimes the low part is here and sometimes it's someplace else, we actually have the low parts going down while the high parts are going up and vice versa. So it's an oscillating instead of a rotating field, but it turns out those are effectively analogous to one another. And we do that by literally just having metallic things that are isolated from one another so I can put distinct voltages on them, and applying a voltage with a time-varying battery, effectively. slightly more subtle than that, but that's really all it is. And that allows us to then have the depth, if you like, of the trap is quite large because it's an electric field interacting with a charge. So often the units that are used to talk about trap depth in this kind of field are in the context of temperature, which you can think of as basically how hot would your object in the trap have to be for it to get out. Okay? The typical trap depth for an optical dipole trap, the sort of tweezers we discussed, is usually measured in millikelvin, so thousandths of a Kelvin, so that's like a part in 10 to the 5 of room temperature. The typical depth of a trap using a charge and an electric field the way we have it is more like of order 10,000 Kelvin. And that's a good thing because it means if you have a room temperature charge in there and it would have to be at 10,000 Kelvin to get out, it doesn't go anywhere, right? But then actually it turns out a step that I didn't talk about at all to actually allow you to get better precision in your measurements is we cool the atom down dramatically so as to slow down its motion. And that turns out to actually involve lasers. But the trap itself is made with what are sort of quasi-static electric fields at some level. They're not the oscillating field of a laser. Yeah, fair question.
So I work with computer hardware, and installing a hard drive is a screwdriver and plugging in 2 cables. When you talked about the students setting up these lasers, like what does it mean to set up a laser?
Yeah. Well, it turns out there are 2 cables, and there is a screwdriver. But there's a few other things as well. So fundamentally, if we were to go back to that picture for a minute, there are efficient ways to do this, but what can you do? Okay, so each of these gray boxes here has 2 cables going in, actually 3 cables going into it. But inside of that, it turns out, is a thing called a laser diode. And if you've ever gotten angry at something like a CD player or a Blu-ray player or something like that and shattered it, one of the things that would come coming out on the sidewalk when you dropped it out of your dorm room or something like that would be literally a laser diode. And those diodes are analogous, and in fact, in some cases in Tiku's lab right now, identical to the ones that we have in these things. It's just a Blu-ray diode is at 405 nanometers, and that is not, unfortunately, the color that we need for all of our transitions, but it's the same little thing. So you run a current into it. That's a commercial device. It's made by people like Sony and other folks. And you run a current into it, and it produces light of a particular color. But what we then need to do is to actually, in a Blu-ray player, blue is good enough, right? What we want is blue with a lot of digits of U after the, after the BL. And so there's a bunch of additional optics in there, but also the current that we have to use to drive this thing needs to be very, very finely controlled. So up above, you can't really see them so well in this picture, but there's a whole bunch of electronics up here behind the blue section in the picture, if it existed, which are also student-built. Things that are sort of controlling the currents we're applying at, I don't know, maybe 10 parts in a billion kind of precision, things like that. So the students are making the electronics, they're setting up the optics, they're machining stuff with Michael in the shop, et cetera, to actually make all these pieces go together. So, like a summer project for a student might be to build one of these things, but there have been many students that have done these kinds of things as summer projects or other parts of larger projects along the way. It's an incremental process. The challenge of doing atomic physics, particularly if you want to do it on a budget, is you can, but there's always an exchange of money for time, right? And another nice thing about Williams is the publication pace of a paper every couple of years or something like that in my field is acceptable as opposed to a paper every 18 seconds if you were at a research university. But it means that we can do the experiment with a lot of really close student involvement and without having to break the bank.
Well, I got another question.
Great.
Your example for the collider, right? So you were showing us like, okay, here's where the Hadron Collider is, and then you showed us this map of like, look at how big this one's going to be.
Yep.
What's the advantage of the bigger collider?
Yeah, that's a really good question. And the problem with the collider idea is that there have been basically no advances in collider technology. That's not exactly true, but there have been no fundamental changes in collider technology in a long time, right? So how does a particle collider work? Well, you've got charged particles which are going, in the case of a circular collider, going around in a circle. And the way you make them go around in a circle is you steer them with a magnetic field. The stronger the magnetic field, the tighter the turns you can make, right? But there's a limit to how strong of a steady state magnetic field you can practically make using superconducting magnets. And the newest state of the art technology is about 16 Tesla is what you could possibly hope to do. And doing that involves cooling the magnets down to about 1 Kelvin and various other things. So it's challenging, right? So if that's the best you can do in terms of your sort of turning radius of your object, then you say, well, okay, fine. Why do I need a bigger circle then? Well, I need a bigger circle because the new collider is supposed to be higher energy, which effectively means faster at some level, although with relativity involved, that's kind of a subtle distinction. But in any event, higher energy particles are harder to turn. They're harder to steer. So if I can only push on them with a certain force using my 16 Tesla magnet, and it's going faster, it means it doesn't make quite as sharp of a turn, and I need a bigger circle to make that happen. And so step one in building that object is to increase the tunnel circumference from 27 kilometers, which I think is what CERN is right now, the Large Hadron Collider, to something which is more like 100 kilometers, right? And why do you stop at 100 kilometers? Well, because that's what the budget maybe would allow you to do, right? If you dig a tunnel under all of France and Switzerland, then you could make a higher energy collider, but you would have to fill the entire tunnel with liquid helium and magnets and things like that as well, in addition to digging it. And contrary to Elon Musk's claims about the Boring Company, it is still expensive to just dig a tunnel, right? In addition to filling it with complicated scientific equipment. So yeah. And there are other ideas. You can make linear colliders as well. The Stanford Linear Accelerator Complex, SLAC, you may have heard of, is an example of this. There's a program that maybe Dave knows more about than I do to make a bigger linear collider, which has other pluses. But it's still, it's a massive engineering project. And absent some fundamentally new and different technology to generate it, the only way to get to higher energies and see stuff earlier to the beginning of the universe is essentially to infuse orders of magnitude more money, which is doable but hard, right? Yeah, John.
How non-linear does your king plot have to be for it to be suggestive of something that might be light dark matter or something?
Yeah, that's a good question. And the answer is, it's not so much about how nonlinear it is, but rather what is the shape of that nonlinearity. There is no nonlinearity in the standard model of physics. That includes things like the Coulomb interaction and regular electromagnetism, as well as the strong interaction and the weak interaction and things like that. But those higher order effects in the standard model, things like, instead of just having the nucleus be bigger, if adding neutrons to it makes it distorted in shape, it makes it look like, I don't know, a banana instead of an apple or something like that, right? That kind of effect on the electric fields will also contribute to nonlinearities in these plots. But if you know something about what the banana shape of your nucleus is, you can calculate it, maybe not with exquisite precision, but at least what should the shape of the S or the U or whatever that nonlinearity be, right? And there's some other characteristic shape associated with this dark matter particle and things like that. And you can probably tease out then, if you have enough points in your plot, the shape of the nonlinearity. And if you see any nonlinearity in a shape that doesn't match with standard model physics, at some level of statistical significance at least, then there's something new and different there. The state of the art in this with ytterbium, where they actually happen to have made halfway decent measurements in a whole bunch of different transitions, is it is clear that there's contributions to the nonlinearity from more than the lowest order term in the standard model, right? The lowest order nonlinear term in the standard model. But it's also pretty well understood that it's just the next lowest nonlinear term in the standard model. So there's no particular reason right now to believe that the ytterbium data is anything other than revealing other pieces of the standard model, particularly because the calcium measurement, which doesn't show a nonlinearity, is at a comparable level of sensitivity. But that's actually one of the other powers of these kinds of measurements, is that you can make an atomic physics measurement in system A or system B that have sort of different, if you like, systematic effects in them. And if you see something significant in both of them, then you start to actually believe it, as opposed to saying it's something that I left the light on wrong or something like that when I made the measurement. Yeah, good question.